Thank you, everyone, for joining this monthly MIDRC seminar. We have an exciting topic today, MIDRC-LOINC mapping, NLPs, and the long tail problem. It is actually my true pleasure and privilege to have Professor Paul Kinahan as our speaker today, accompanied by his PhD student, Zihan Li. Dr. Kinahan is a professor of radiology and bioengineering and the vice chair of radiology research at the University of Washington in Seattle. He is also the head of the Imaging Research Laboratory and the clinical director of PET-CT imaging physics. His research includes optimizing the physics of PET-CT imaging, the use of image reconstruction methods, objective assessment of image quality, and the use of quantitative analysis in image-based clinical trial, which he has been a leader in this area. He's also a founding member and chair of the NCI Quantitative Imaging Network, and more recently, he's the director of the Imaging Core Lab for ECOG Akron Cooperative Group. He also served as a president of the American Board of Science in Nuclear Medicine, and he has received numerous awards for his contribution in medical medicine imaging. This most recently is the IEEE MPSS Edward J. Hoffman Medical Imaging Scientist Award for technical contributions and education. Dr. Kinahan as well is the co-PI of the MIDRC grant. This is the, as you know, the multi-society, multi-center initiative with Dr. Mary Ellen Geiger. We're very much looking forward to hearing from Dr. Kinahan. A little bit more about Zihan Li, who is a graduate student in the Dr. Kinahan lab. Despite his young age and early career, he has quite an impressive resume already that includes application in vision language models, foundation models, and medical imaging analysis. He already published 10 papers in prestigious journals and conferences. That includes the IEEE transaction in medical imaging, MACAI, and he was also a finalist for Best Paper Award at MACAI 2023. He also serves the community as a reviewer for several international journals and conferences. Dr. Kinahan, the floor is yours.
Thank you so much, Issam. I really appreciate the introduction. I'll share some slides. And the way we will do this is I'm going to give a brief overview of the topics about harmonization of study descriptions and what we've been doing manually and why that doesn't solve the long tail problem. And then Zihan will have a presentation where he's actually done all the work on coming up with AI-based methods to solve the long tail problem for the study description harmonization. And very briefly, just to measure to some acknowledgements for the support from NIBIB and ARPA-H, the MIDRC Data Quality and Harmonization Subcommittee, the Technology Development Project 3B Group, Mary Ellen Geiger, Adam Flanders, George Shee, Emily Townley, and Issam and Peyton for helping to moderate the session today. So as maybe a one-slide reminder of what MIDRC is, and I'm not going to read through all of this because the first line is the most important, is that we have a curated image and data commons. And the goal of the curation is that, as the top left shows, we get CT and X-ray images and other modalities donated. These will go through a curation process, and the curation is essentially providing information about the images to help people with cohort selection if they're doing AI or machine learning algorithm development. And some of the updated numbers there at the bottom, as of the end of November, there was over 500,000 imaging studies included in MIDRC now. And so our goal of the data quality and harmonization is to harmonize the incoming data to help people with selection. And that means providing information about the quality of data. And that would facilitate both accurate and simple cohort selection, as I mentioned. This is a very high level view of the MIDRC data flow process. And on the bottom left, you'll see the DICOM image set is coming from a contributed site. And that's generally processed either by an RSNA or ACR technology stack using their clients. And then that's uploaded to MIDRC or to basically within the RSNA or ACR, where it's being reviewed for de-identification. And then it goes through further detailed review to make sure that all the public or protected health health information is removed, and potentially annotations are added, but we won't be talking about that here. Finally, the images that are considered fully de-identified are the information about them from the DICOM headers is abstracted into an image manifest, and that's what's uploaded into the data model, which is maintained by the Gen 3 data group, which enables people to select the data for download. And so from the Cohort Explorer, an external user on the right would query the Cohort Explorer, find the studies they want. From those, they'll get links to the DICOM images they want, and then they can pull the images and download them directly. And what that looks like is, here's an example of the DICOM Explorer, and it might be a little small to read. I'm sorry, but this was the biggest I could get it. Is you can look through the images. Currently, there's 184 exams or studies that have been released for download, and you can sort by a lot of properties, including the study description or things related to that. However, one of the challenges is that the study descriptions are quite variable. It's free text that's entered into the DICOM header at the time of the data acquisition by the scanner. And on this slide, you see a data set that was analyzed. So the 4 columns are the modality. So we have a bunch of X-ray radiographs, DX and CRs. There's different study descriptions that go along with each modality. And we see the number of exams with that study description. So the first one had almost 16,000, which accounted for almost 11% of all the data. And you can see this going down the list. And to get up to 99% of all the data, we had to go down to, this is row 444. So 444 study descriptions accounted for 99% of the data. However, it goes on much longer than that. You see that at row 1385, the last one, there's almost 1,000 more rows, and this was from an early study showing the long tail problem, which is what we're looking at here. So we can manually look at the DICOM metadata, look at the study descriptions, look at the modality, and make assignments, as we'll talk about left. But we can never address this long tail problem, not manually. And we'll come back to that later. So the terminology we use for harmonization is we looked at a combination of something that was developed independently by the RSNA RADLEX group, specifically what they call the RADLEX playbook, and also separately from the Regenstrief Institute, the LOINC codes, which are part of the UMLS, and it's a maintained vocabulary that we'll talk a little bit about that. So the LOINC codes, these are used across all of medicine, such as lab medicine, both to order tests and results. And it was a terminology or controlled vocabulary, I should say, developed by the Regenstrief. And a couple of wonderful things about it. One is that each row here corresponds to a LOINC code, and it's unique, and it's maintained in the LOINC database. The other thing, as part of the joint RADLEX playbook and LOINC thing, is they develop the long common name, which is very similar to a study description, but also includes the modality as well. So like the very first one, if you can see, it says CT chest. This is also unique, and it's generated by an algorithm, but it's human readable. And there's a one-to-one mapping between the LOINC code and the LOINC long common name. And there's other information that's contained that's very useful for study selection, such as the modality, whether contrast agent was present, the region of the body or anatomy, things like that. So we created the MIDRC-LOINC mapping table, which I've talked about in this seminar before, I think a couple of years ago when we were first getting started. And you see what happens here is from the DICOM data, we take the modality and the study description, and we map that to a LOINC long common name, which has a corresponding LOINC code. And the interesting thing here to point out is that there's about 10 or so different study descriptions that are all different, but they all map to the same LOINC long common name. So in other words, if you're really interested in a CT chest without contrast agent, you use that as the LOINC as a descriptor, and it'll find all the studies on the left, which are indeed CT chest scans without contrast. It's just named differently by the sites contributing data. When we use that, now we get 99% of all of the study mappings done in 22 descriptions using LOINC long common names. Whereas a reminder before, when we were just using study descriptions, we had row 444. So we've really compressed the number of descriptors needed to select the data. So that was a huge success, and we're continuing on with that work. However, it didn't get rid of the long tail that I pointed out. This only addressed the very first part of the curve where we have the most studies, but there are thousands or tens of thousands more study descriptions which can't possibly be handled manually. And so we need helper AI methods that Zihan will cover next. And I just wanted to mention briefly that if you're willing to donate data to MIDRC, please go to MIDRC and go to the donate button, and we'd be more than happy to take in images and de-identify them for the common good. So with that, I'll stop there and turn it over to Zihan.
Thanks for Paul the introduction. And this is for our project. It's called the multi-stage multimodal deep learning for harmonization of radiology study descriptions. And basically, we utilize two different approaches based on the state-of-the-art models. The first one is called the BERT model. It's one of the NLP methods, and we modify it to the multi-stage classification, and we call it MFNet. And then we modified to add some radiological region classification based on the image segmentation method, such as the total segment, and we call it MFNet version 2. And we utilize the DICOM head data for execution. And then we will introduce the MGLL, the multi-granular language learning. It's an image-based model using the natural language supervision for training from labels. That means we doesn't need the DICOM head data for execution, and we fine-tune it using the nonlinear codes. Then we can introduce the MFNet. As we can see here, our input for the MFNet is the study description, body part, modality, and institution ID. And we developed 4 different BERT models. The first BERT model will classify the study description into the 3 types of the modalities. The first one will be the XR, and then the XR portable, and then the others. As we noted here, the other modalities is primarily the CT modality. And then for each of the BERT model, we will classify the DICOM case into the different nonlinear categories as here, such as the XR chest AP, portable XR abdomen AP, or CT chest without contrast, such like that. And we can see here, for the MFNet version 1, there are some questions needed to be addressed. So, for example, there are some sources of the errors in the input data. For example, we have some the missing data here, about 22%, and we also have some incorrect data in the body part. That's why we need some more concrete method to identify the body part region. And then we introduce the MFLAT version 2. We can see here the new component in the MFLAT v2. We utilize the total segmenter here. And for the MF version 2, we also have the 3 stages here. The first stage will be classified into the 3 different modalities, the XR, portable, and others. Then for the stage 2, we can have the initial learning code prediction as here, but we also have some low confidence cases, such as we have the low confidence, and then we will transfer these cases into the stage 3. And during the stage 3, we will utilize the total segmenter to define the body part region. As here, we have the image scan, and we encode them and decode it into the 3 different body parts. For example, the abdomen, chest, and pelvis. Then we will add this information together with the original patient exam level features. Then for the stage 3 BERT model prediction, and finally we can get the final learning code prediction. But if there are still some low confidence cases in here, we will ask for the human expert for the feedback. And I will introduce some total segmenter briefly. Total segmenter is a state-of-the-art tool designed for the precise and robust segmentation for the structures in the CT images. For example, here we can segment over 100 organ structures in the CT images, but here we only need 3 different body parts. As we can see here, we will have the chest body part, we will have the abdomen body part, and the pelvis here. For the chest, we should include all of the lungs. So we have the 5 labels to identify the chest. For example, the non-upper lobe left and the lower lobe left here. And we also have the 3 different body structures to identify the abdomen part. So we have the kidney right and kidney left and the liver. And finally, we can identify the pelvis. We could utilize the hip left and the hip right to identify him. So basically, we will input an image scan into the total segmenter, and the total segmenter will output some mask, some segmentation output, and we will classify the image scan based on the mask output based on the segmentation output. And this is for the results between the total segmenter and other whole body segmentation methods. We can see here, so total segmenter can have a better performance compared with other whole body segmentation methods. For example, the STU-LAT and the MO9 and the MPUM. We can see here. So overall, we can get 100% accuracy for the body part classification. That means the 57 over 57, and the STU-LAT could be worse, and the MPUM will have the worst performance here. Then we can compare the results between the MF, the V version 1 to the version 2. That means we could utilize the additional body part information from the total segmenter. We can see here for the results between the different stages on the validation set, the error rate on the CT image could be reduced by 50%. And we also have some results in the test set here. We can see we have less low confidence results. That means we can get more accurate results with the changes of the MF version 2. And then we compare the the BERT with the MF version 2, we can see that so we have the much less than the error cases compared with the BERT. So in the original BERT model, we will have the over 300 error cases, but in the MFNet version 2, we only have the 1 error cases. That means we can get a better performance, utilize the multi-stage classification pipeline. And then I will introduce the multi-granular language learning. That is the briefly comparison between them. And for the model architecture, we utilize in the MFNet version 2, we utilize the Zihan and the transformer, but in the MIDRC, we only utilize the transformer. And for the feature extraction, we utilize the total semicolon for the region encode and the BERT for the text encoder. But in the MIDRC, we also utilize the clip region encoder. It's also one type of the transformer model. And for the training method, we utilize the masked language modeling in the MFNet version 2, but in the MIDRC, we utilize the contrastive learning. And what is the most important thing is that we utilize the training, we utilize the image and text for the training data in the MFNet version 2, but the text will be the primary. But in the test data, we also utilize the image and text for the testing in the MFNet version 2, but in the MIDRC, we only utilize the image for the execution. That means we do not need the text description, and we can only get the precise logic code based on the image only. But here for the present, the MIDRC only applicable for the 2D image, for example, the X-ray, but for the MFNet version 2, we could applicable for the 3D and plus the 2D. Then I will introduce the multi-granular language learning here. So basically, its basic idea is from the clip, the learning transferable region models from the natural language supervision. And here we have the large amount of structured data or tabular data in the metadata. For example, we have the modality, we have the series description, we have the study description. In our opinion, it's belong to the different different granularity. That's why we call it the multi-granular language information here. And we have some the motivation here. So we want to learn some, the image features from the language. So we have the tabular data, and then we pre-train the model. Then we fine-tuning the model with only images as the input. And we could get some downstream tasks such as the data harmonization, and we have some example here. So that's why put the right load here. So we doesn't need the metadata such as the description, and we test the image. We could get the accurate logic code here. So that is the portable XStar chest AP single view, and that means we could notice the slight differences between the different logic code. For example, we could notice the difference between the chest and abdomen, and also notice the difference between the single view and the chest views here. So the pipeline illustration are here. So we have the metadata, and we also get the images for the contrastive learning for the pre-training, and we could get the pre-trained model weights. Then we will re-input the image for the fine-tuning task, and we will get the ground truth. For example, here it will be the logic code to supervise the fine-tuning model weights, and then we will evaluate the fine-tuning models and finally get the results here. The pipeline will be here, so we could get have some text here. So for example, we have the CRXR portable chest one view, and the initial only CRXR AP grid, something like that. And we also get some of the image here. So basically, here we will conduct the contrastive learning, and we will have the design it for the different level granular language information each, but it will be it will all be encoded for the same text encoder, and the image will be encoded by the clip image encoder here, and we will get the different features here. As we can see here, we could get the V1, V2, and Vn for the image feature, and we could get the T1 and the T2 and the T3 for the language information feature. Then we will conduct the three different supervision here. So we will have the point-wise supervision. It's like a binary cross-entropy loss, and we will have the image supervision and text supervision. It will be the info NCE loss. Then we will conduct the KL loss, KL divergence loss, and we want to push the three different the granularity features into the meaning. Into the mean feature of all the different granularity features here. So, and this is for the pre-training pipeline, but in our validation and in our test, we could only utilize the image. That's because we have already built the bridge between the image and the text, and we have connected the image information with text information. That's why we could only utilize the image information only for the execution and to get the non-linear code prediction. The dataset will be driven by the MIDRC dataset, and we take 2D images as an example. We collect over 170,000 image text pairs, and we could collect here like that. We have the modality and the study description and the series distribution, and we want to do the data harmonization for get the final long common name here, XR port chess AP1 view here. And there are some preliminary experiments, and we load here is for only 2D images, and for the train set we have over 89,000 cases, and it will be classified into the 40 categories. And for the X-supportable, we will classify them into the 6 categories. So we could see the result here. So on the test set, we could have over 99% ORC, and also we could have the over 99.75% for the ORC in the X-supportable category here. That means we could get basically the comparable performance with the MFLAT version 2. So the summary here, so both MFLAT version 2 and MGL could work very well. That's why we put the size here. But we also think the MGL may be preferable because we do not need to rely on the DICOM head data. That means more general, and we do not need the labeled for the pre-training. That means we could utilize as many as the data, and we could easily adapt it to the other modalities. That's our feature work. That's why we want to make the MGL adapted to the 3D images such as the CT or MRI. So for the future work, for the MFLAT version 2, we want to evaluate with more new data and make adaptation to the image series beyond to the image study. That's why we want to focus on the series description here. And for the multi-granular language learning, we also want to evaluate with more new data. And another thing is important is that we want to make adaptation to the 3D images for the CT and MRI, something like that. And that means we could utilize more data for the pre-training and get more accurate output here. And I think that's the end of all my presentation. Thanks here.
Thank you very much, Zihan. Thank you very much, Paul. Start with some of the QA. I think I have the question from Dr. Clooney. How effective is the model at IV and oral contrast detection? especially from the images?
Okay.
Thanks for the question, David. We haven't tried that yet, basically. So in either, so the multi-granular language learning, I know we haven't tried it. It may be challenged there because it's a projection image, and that we have so far with we would expect maybe it would work better with fully tomographic 3D volumes, because we'd have better contrast within the image, but we just haven't tried that. I'm just trying to think how that would work within the first approach with the MFF-net version 2. That's actually worked pretty well because the as you saw, the descriptions and of the LOINC long common names indicate whether or not there's contrast present or not. But there, of course, we're also relying on the information in the DICOM header as well too, if it's present. I hope that answered your question.
Great. Another question, did you compare your solution with some of the commercial solutions like Analytic? That's also from David.
No. We'd love to, but we don't have MIDRC does not have an agreement that I'm aware of with Analytic, and it would be interesting to see how that works too.
Okay.
Ours is, by the way, and ours is intended to be open source as well. It's all on Git.
That's a major advantage and
that,
contribution to the community, much
one big
appreciated.
difference. Yeah.
Of course. Another question from Ken Wang is on whether the total segmenter can deal with the problem of organ inclusion and partial organ inclusion or occlusion, practically could be the challenge.
So I think I understand. So I'll take a stab, and Zihan, you correct me if I'm wrong. So based on discussions with our radiology colleagues, say for the for a chest scan, we're trying to figure out, well, what's an appropriate algorithm to be sure that we have the entire lung. So what's buried in the details of the algorithm is, say, for the chest scan, there has to be a slice that's above the lung that contains no lung. And then at some point below that, there has to be a slice with lung all the way down, and they all have to be contiguous. There can't be any gaps running inferior till we finally get to another slice that contains no lung. But in between that, there's contiguous slices that contain lung. And we felt that was an accurate way to say that we have completely captured the lung, which was what we were using as a definition for a chest scan. We're happy to adapt that if there's other suggestions, but and similar rules were used for the abdomen and pelvis.
That goes from one of the initial questions that actually I missed from Dr. Fogel. Would you consider this segmentation or chunking?
I think that might have been for the early MFF-net, where the studies, the BIRD algorithm that Zihan, I think, correct me if I'm wrong, the first step was to decide what type of modality was it. And the modality decision was either an XR, combining DX, CR, and everything, or portable, because that was a big class, or others. And others was primarily CT, but it could be MR or nuclear, things like that. So I guess in that case, division or chunking might be a more appropriate word than segmentation. The segmentation was used later to try to come up with a radiological classification of the image, chest, abdomen, pelvis, like that. I don't know, Zihan, does that sound correct to you?
Yeah, I think that's correct, because we do not need the much better the segmentation performance. We only need the radiology structure classification. That's why we only want to identify the lung, pelvis, or the abdomen, such like that. So, and we admit there are some of the failure cases in using the total segmenter, but I think that is acceptable for our study, because we only want the radiological structural classification and not the segmentation, accurate segmentation output. Yeah.
Right. Thanks.
Another question is actually related to the language models that you used. BERT is an autoencoder design. There are other out there architectures that are like Llama from Meta, Gemini, I think it's BERT on BERT, and GPT, which is a decoder design. Would these have different performances? Have you experimented with these?
Yeah, I can answer the question. So yeah, there are some large language model here, but we think because I think it is something like the easy text classification, and we do not need such much power for the large language model to do the classification. Another question, another issue that why we do not utilize the large language, because the logical code the difference between the different logic code it is slight. That means it is difficult for the large language model to capture the differences. That's why we need to fine-tuning the large language model to capture the slight differences between the different study description and the logic code. And it will cost much, but I think as we can see here, we could only utilize the BERT model to get over 99% accuracy here. So that's why we do not explore the large language model for the task classification here. Yeah.
Issam, if I could just go back to one point too, I just remembered, and the question about do we have complete organ inclusion and things like that, where we use total segmenter. We actually, total segmenter is not a perfect algorithm by any means. It's known to fail for some objects, which is why Zihan did the extra testing to compare it against other sort of state-of-the-art algorithms. I think the case here that we have is not only is that we're really asking it for a much simpler problem, or we're giving it a much simpler problem than, say, segment everything in the body. We really just want to find out what region of the body are we covering, and are we covering that? And there's some cases we could imagine as time goes on that there will be some things that we need to add some other organs or body parts in for extra redundancy to be sure we really are getting that approach. We're not trying to claim that we've segmented out the liver accurately. We're just trying to say what region of the body have we covered. That's a nuance which makes us feel more confident about the use.
There is a comment about the chest scans needing adrenals due to METs.
That's a good question. Yeah, I was wondering about that. I took note of that, and we're going to confer if that's really what if our radiology colleagues agree that's what's also needed, in addition to being sure that we've covered all the way to the very bottom of the lung. Then we would certainly add that. That was a good point. I did note that too. Thanks, Issam.
Okay, great. What's the effect of age on performance? Did you look, for example, I don't know if the data has pediatric versus adults that you were able to look at.
Ooh, that's a good one. No, we haven't. Zihan, we haven't looked at that, have we?
I don't think so. Yeah.
No.
Yeah.
Yeah. There's lots of things we could be doing that's a good one.
Okay.
Sorry, Issam, and one thing I forgot to mention, we given the fact that there's tens of thousands of study descriptions already, and we can't go through manually and compare them to the images, and also even if we did, as new images come in, there could still be errors or things with new data coming in. So one of the nuances about this harmonization process is we're trying to, there's error bars on what we're doing. So, what we haven't succeeded yet is giving sort of some level of confidence interval. So, if we predict a LOINC long common name, how often are we right? And that's a key thing that we need to do in some further testing. But it seems that likely that there will always be some errors no matter what.
Okay, great. One question I want to ask you, did you look at this histogram that you showed at the beginning, the long tail problem, after doing the harmonization, how it looks like? One thing that comes to mind when you're looking at accuracy for the harmonization, that the rare events, the tail itself, may still not describe it properly.
Sorry,
That is driven by the majority typically.
I'm sorry, I didn't quite follow your question, Issam.
Did you look at the histogram after you did the harmonization, how it looks like? Some of the rare events that you mentioned, tail problem,
yes. Oh,
would
sorry.
still be
Yeah.
problematic.
Right. Yes. So the histogram changed shape dramatically because the way and one of the details in our process is for our manual classification. Right now, we arbitrarily adopted the rule that for us to go through and manually work out a classification with a LOINC long common name, there has to be 10 or more studies with that name in it. Otherwise, we don't tackle it. So anything with 10 or more studies has been really compressed, making a much more skewed distribution. The tail after that is untouched because we don't. But now, how the shape of that would be when we then include either of these methods to do the classification. No, we haven't looked at that shape, and that's a really good point. Thank you.
Given your expertise in nuclear medicine and PET imaging, when applying these techniques to nuclear medicine, do you think they would perform similarly to what you've shown in X-ray and CT images? Given the
hard to say. We don't have much data. Well, I guess there's two parts to that. One, within MIDRC, we just don't have that much data yet on nuclear medicine techniques. We would probably focus first on MR. Based on my own experience, there's less variety of procedures done within nuclear medicine considerably than there would be within X-ray, in particular in CT. CT has a very broad range of study descriptions or types of exams. Within the LOINC system, there's something like 9,000 long common names, and we're only using a few hundred of those. But that's part of the tension that occurs in this process. So the study descriptions or even series names locally generally work fine because it's a local institution. If you say, well, it's our standard protocol with Dr. X's modification, or we've added a scan, that can just be typed in. And then to my experience, that rarely causes confusion locally within the institution where the scan was acquired and then was read out diagnostically. The challenge is when you're trying to pool this data from multiple centers with such a wide variety of study descriptions that are entered essentially manually, or they're free text at least. How can you reduce that down to a manageable number of harmonized study descriptions? And so we deliberately focused on that by saying that we're trying to keep the number of new LOINC long common names we introduce as low as possible in order to make it easier to do the cohort selection. But then that's also going to necessarily give less information than we could about some studies because we're lumping them together. We're being more of a lumping operation. And where that fits in is that, as we go through helper AI-based techniques, we will need new methods. So that's one of the reasons Zihan built in a confidence estimator as well, too. So, through these, it produces an estimate of the confidence of the prediction. And if it's low, we check it, and we may need a new LOINC code. So sorry, that's a very long answer. I hope
No, that's great. I think we reached our time. Emily, you can correct me on that.
Nope, that's great. I think we're about done.
Well, I would like to thank Dr. Kinahan and Zihan for a wonderful and informative presentations, and see you next month.
Thank you, Issam.
Thank you, Sam.
Thank you, everyone.